Hello everyone. In this video, we're going to analyze the runtime of the table doubling procedure we introduced in our previous video. So here we have some actual code that performs the table doubling procedure. Let's quickly look at it and make sure we understand what it does, but this is a simple sort of thing you could probably write in your first programming class if you tried for a while. So let's check what happens. At the bottom of this code, we have the actual insertion, which is taking place. I don't know how it did that, so let's take a second and delete that. So we have the actual insertion. And the part above it is doubling when necessary. So we have a couple of variables. X is the thing we are inserting. A is the array, which has a capacity of m. And n is the number of things we have actually inserted into the array. And then we need to double if the capacity is equal to the number of things in the array before we insert. So if we have reached capacity, we must increase the capacity. So we create a new array, and then we copy it over, and then increase the capacity. Simple as that. Nice, easy code. How are we going to analyze this, though? Because we might notice that the cost of one insertion varies a lot. So we notice the cost of this function varies with n and m, which is a peculiar thing. And in fact, most of the time we would hope that we don't get into that if statement if n is equal to m. So it would typically take a constant amount of time, so we're just doing basic assignments at the bottom there. But that's not quite doing it justice, because when we double it, it costs a lot to do that doubling process. So let's try and analyze what happens here. The way we're going to do that is by imagining how long does it take to do many insertions. So we're going to sort of be doing a average case analysis, but in a different way than we've done in the past. So how are we going to do that? The way we're going to do that is we're going to create a table that has the number of elements in the array, the capacity of the array, that's that m variable, and the cost of the operation to do the insertion. So, following our procedure that we introduced in the previous video, and is demonstrated in the code above, what we're going to do is we're going to start with a capacity of 2. Let's say we had one element in the array. The cost of an insertion at this point would be some constant c, because all we're doing is those last couple lines of code. Once the number of elements increases to 2, the capacity needs to change from 2 to 4. The cost of that is going to be 4 times whatever cost it takes to copy memory. Why is it 4? Well, we're going to have to potentially allocate memory and reserve memory for each individual element in the new array. In fact, for something like open address hashing, we would have to do this. So just to be safe and generic, we'll say it costs 4c for the increase in capacity and c for the insertion. And then we would have a third element, and our capacity would be 4 still. That's going to be constant. We then have a fourth element, and we need to increase the capacity from 4 to 8, which would cost 8c plus c. And now we actually start to reap the rewards of this strategy. For 5, 6, 7, and 8, this would have capacity 8, 8, 8, and then 8 to 16. The costs here would be constant, 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 16c plus constant. And if we kept doing this until we had n insertions, for the sake of argument, let's pretend that we would have n going to 2n here. So we're pretending n is a multiple of 2. Not that it really matters too much, but we'll include that for now. And the cost of such an operation would be 2n times c plus c. So, let's try and compute the runtime of this thing, of doing n insertions. How are we going to do that? Just add up the cost column. We've done something similar to this when we did some probabilistic analysis in the past, and when we did it in the past, we also had the probability of doing the operations. This is the same as that sort of analysis, but we're ignoring probabilities of this. We're imagining we're doing all of these operations. So, T of n is equal to, well, I have a c for every single insertion. So I have nc guaranteed because I'm doing n insertions. So we have n times c out front for sure, plus the cost of doubling. That's those steps where I actually needed to reallocate memory. So, what is that cost? That cost would be, well, the first one was 2c, plus the next one was 4c, then 8c, then 16c, then eventually we would have an nc, and then a 2nc. We may have seen summations like this before, so let's try and analyze them the same way we did in the past. So we rewrite all of those additional terms as 2nc plus n times c plus n times c over 2 plus go down until we get down to that last element, which is 4c plus 2c. Then we factor out the dominant term, which is 2nc. We have 1 plus a half plus a fourth plus all the way down until we get to 4 over 2n plus 2 over 2n, which is less than or equal to nc plus 2nc times 1 plus a half plus a fourth. This infinite summation that we've seen 8 quadrillion times at this point. This is equal to n times c plus 2nc times that infinite geometric summation adds up to 2 we've seen in the past. So this is equal to 5cn. So some constant, 5c, times n. So it's in big O of n. It's really easy to see that it is in big omega of n, because the summation there is just greater than or equal to n times c. So T of n would be in theta of n. But this isn't what we want, actually. This is the cost of performing n insertions. We want to know the cost of one insertion on average, but that's not really reasonable to ask, so we're going to do what's called an amortized analysis, where we say the cost of several operations is theta of n. What is the cost of one operation? We can do that by taking the total cost of all of the operations and dividing it by the number of operations. So the cost of one operation, the cost of a single insertion, in a sort of average sense, should be the total cost. Let's say it was bounded above by 5 times c times n, that's an upper bound, over the number of times we inserted, which was n, which is equal to 5 times c. So, doing n insertions, if we think about what is the cost on average over all of those insertions, well, it's constant. It's bounded above by 5 times c. That is to say that the cost of a single insertion in some sort of average sense is about theta of 1. About constant runtime. Which is theta of 1. For certain applications, that might not be good though, because if you have security critical operations, let's say you're designing software for a fighter jet or for an airliner, or something where quick responsiveness might be critically important to people's lives, you might not want to tell someone using your software that it takes constant time, because it does not always take constant time. And for something as low level as this is something that will happen potentially at the programming language level. When you're implementing a programming language, you might have this. You want to know exactly how this is happening. And if you're designing your own data structure, you might need to know exactly how long these take for sort of security critical operations. So this is worth mentioning that even though we can expect it to take theta of 1, almost all of the time it does, it's just some of the time we have to double it. Especially for large arrays, that's the case. It may not be a sufficient description of the runtime for certain applications, especially those which are critically important. So that's worth keeping in mind. This is effectively the idea of table doubling. There's actually nothing particularly sacred about doubling the size of the table. So it's not super important that we remember that we doubled it. It's just that that's the standard way of doing it. We could have tripled it, we could have quintupled it. It didn't really matter too much. So this is a very useful application of what's called amortized analysis. You may see this going forward in future applications, but for now, this is really all we need to know about it. It's possible that we can implement the same functionality for something like a hash table or something like a heap or any of the data structures we've discussed in the past. I'll leave those applications to you. That way I can potentially reserve them for future exam questions as well. So that's about all we have to talk about with table doubling, and hopefully it doesn't seem too bad of an analysis. Whenever you're doing this sort of analysis, you're going to create this table here, and then analyze the resulting summation from that table.